So it's the number of pairs that satisfy these two conditions. Okay, so you got an idea now of what n stands for, the number of reversed pairs. And the pairs, remember, are just any two of these such that the first one is less than the second. And you'll have 10 possibilities, right? So I assume you're familiar with that now. Okay, now as homework, as exercise, I ask you, for this permutation, just call it y, it's a different one, right? These numbers here are different. 1, 2, 3, 4 get permuted to a different ordering, if you like, different permutation than this one. Homework, find in y, find the number of reversed pairs for this permutation. Now, okay, so you know x and you know y, so we can now perform two permutations, first x then y, right? First x and then y, and then I ask you what is big N of yx? Right? In other words, how many reverse pairs does it have? Now, I'll give you the answer, but I ask you to do this kind of thing for this case as homework, right? Give you practice on how to do it, and then do it, and then calculate x followed by y. So this followed by this, and then with that result, that new permutation of yx, calculate the number of reversed pairs that it has, okay? And you'll find the answer is 5. Right? Now for x it was 6, for y, n of y it's 5, and n of yx 5. Now, is there a relationship between those numbers? Well, in general, if you have two permutations, x and y, and if one of them, well, let's say, well, I'll be specific and generalize. Here I'm generalizing later. I'll be specific now. Now look, n of x was 6, that's even, okay? And n of y is 5, is odd. And n of the product, when you have two of them, also odd, okay? Now, that's a general result, and here I'll give the proof. It's theorem 41, but here's a general result. So, if you have a permutation x and another one y, and if n of x, remember n is the number of reversed pairs, okay, for that permutation x. So if nx is even and ny is even, then n of xy is even. Okay? And well, you've got this tables. So if nx is even, ny is odd, then n of xy is odd. So are you getting a bit suspicious about what's going on here? I mean, how do you derive this from these? And if it's odd and even, again, odd. And if it's odd and odd, you get even. So how are you getting this n of xy from these two n's? It looks as though, I mean, look, it looks as though you're adding them, right? Somehow, it looks as though this n of xy is the sum of these, or sort of, right? Because if it were the product, if you were multiplying these two things, if you multiply two evens, you'll get an even, that's okay. But if you multiply an even with an odd, you'll get an even. But no, you get an odd here. And similar here, with the same surprising result. And if you multiply an odd by an odd, you'll get an odd. But no, you've got even. So it looks as though this n here is some kind of sum. You're adding these two, because, watch. even plus an even gives you an even plus an odd gives you an odd, odd plus an even gives you an odd, odd plus an odd gives you an even. So it sort of fits. So imagine you're Marcus de Sautoy and you're playing with this for the first time, and then you get suspicious. Okay, this maybe is somehow the sum of these. So you may formulate something a bit like this as a possible theorem statement, right? And now in the text, theorem 41 is you take any two permutations of your symmetric group over applying permutations for over little n objects, this little n here, okay? Then you'll get this is true, okay? So minus 1 raised to this power is equal to minus 1 raised to this sum, okay? All right, so how to prove that? And I should say, when I was studying the text to understand the proof, to be frank, I was not happy. I thought occasionally Barnard does not do a good job. I was feeling rather antsy. I eventually understood what he was saying, but I had to rework the formulation of his proof. So what you're getting here is more my take, based on his broad ideas. If you choose to just read his proof alone without this sort of visual aid, I think you may end up getting what I had, and I call it brain strain, right? I was having a hard time. It took me a while. I had to figure out for myself what's going on, taking his clues and then combining the two, and eventually, that's what it's about. Okay. All right. So here's the proof. So we're trying to prove theorem 41 that this result is true, and what you see here is a mix of Barnard's approach and mine, and I'm saying this myself. I feel this mixed approach, his and mine, is a lot clearer, right? So, okay, all right. So in general, we have m of these pairs, right? Which pair? No. M pairs in general, right? So for 5, if you have 5 objects, you'll have 10 pairs, okay? So this M is not these pairs, not reverse pairs, but just pairs in general. Before whether you check whether they're reversed or not, right? So M for 5 objects would just be 10. It would be these 10, okay? So that's M. Now, apply your first permutation, X, right? And so here are all your pairs, and this n of x here is the set of reversed pairs. Okay, so you've got all your pairs that you start with. You apply your permutation X, and you select this set. In this case, I'll do it now. It's a set, the size of the set. Okay, so you find this set, and it's the set of reversed pairs, like here. Okay. Now the pairs that get reversed put in here. This subset, right? I'm using a Venn diagram. So this is the situation after you apply your first permutation, which would be X, right? So your set of pairs will split into two categories, right? Those inside subset N, right, that are reversed, and the ones outside are the non-reversed. Okay, that's fairly clear, I guess. All right. Now you take this situation, and now you apply to all these pairs. You apply y.